Imagine like deciding to build this massive towering skyscraper, right? You've got the funding secured, you've hired this top tier construction crew, and all the heavy machinery is just sitting on the lot, engines idling.
Sounds like a pretty solid start, actually.
You'd think so, but then instead of handing the foreman, a detailed set of architectural blueprints, you just hand over a napkin. Like a napkin with a vague, squiggly drawing of a tall rectangle, and you just say, hey, make it look something like this.
Oh, wow. Yeah, the structural integrity would be compromised before they even finished pouring the foundation. I mean, you'd end up with a very expensive, very dangerous pile of rubble.
Exactly. And yet, that is precisely the approach so many people unknowingly take when they first dive into scientific research. They get incredibly excited about the data collection phase.
Actually pouring the concrete, basically.
Right, pouring the concrete without ever taking the time to draft a rigorous blueprint. And in research, that foundational blueprint is your research question. So, welcome to this custom-tailored deep dive designed specifically for you.
We are so glad you're joining us.
Today, we are looking at a stack of course material all about formulating the perfect research question, specifically focusing on mastering Lecture 2. Our mission today is to just strip away all the academic jargon and show you exactly how to build that blueprint.
It's so important to get this right. Research methodology often gets shrouded in this heavy, intimidating academic language.
Yeah.
But honestly, if we dismantle it, it's really just a logical sequence of problem solving.
Yeah, it's like taking raw curiosity and sharpening it into a precision tool. And to make sure you have absolute mastery over the concepts, we are going to use the 30 multiple-choice questions from your material as our guideposts. We'll break down the logic so you understand the why and how behind every single correct answer.
I love that approach. It's about taking that raw curiosity and making it actionable.
Okay, let's unpack this. Let's start right at the very beginning with the overall life cycle of research.
Yeah.
I think we often assume research starts with a sudden eureka moment in a lab, but the material suggests something much more methodical.
Much more. It's a process.
Right. So if we look at question 6, it asks, what is the first step in the life cycle of research? The options are A, spell out the research question, B, formulate the objective of the study, C, identify the data needs, or D, choose the study design.
And the correct answer here is C, identify the data needs.
Really? Because I feel like people instinctively want to jump to option A and just write the question.
Oh, absolutely they do. But logically, before you can formulate a question about a problem, you first have to recognize that there is a gap in your knowledge.
Like a missing piece of the puzzle.
Exactly.
Yeah.
Say you have a patient with a strange symptom, and you realize, well, we actually don't have data on this specific presentation. That realization identifying the missing data, that is the actual spark that initiates the whole process.
That makes total sense. You can't ask how to find a missing puzzle piece until you noted the hole in the puzzle. So let's trace that through the rest of the cycle. Question 28 asks, in the life cycle of research, spelling out the research question is followed by what?
Okay, what are the options there?
We've got A, preparing data collection instrument, B, formulating study objectives, C, collecting data, or D, formulating recommendations. Based on the sequence, it has to be B, formulating study objectives, right? You have the question, so now you need the specific goals.
Precisely. The objectives are those actionable steps you will take to actually answer the question.
Okay, so that leads directly to the ultimate goal of any study, which brings us to question 19. It asks, which is the last step in the life cycle of research?
And let me guess, the options of the remaining steps.
Yeah, exactly. Spelling out the question, formulating objectives, formulating recommendations, or choosing the design.
The correct answer is C, formulate recommendations. I always tell people research doesn't exist in a vacuum just to generate spreadsheets,
Right, nobody wants just a pile of numbers.
Exactly. The final step is always taking your data and translating it into actionable advice for policymakers or clinicians or the public.
So zooming out, question 1 essentially summarizes this entire machine. It asks, which of the following is an element of life cycle of research? A, identify data needs and spell out the research question. B, formulate the objective and design the study. C, draw a conclusion and give recommendation to stakeholders. Or D, all of the above.
And given what we just discussed, the answer is clearly D,
Yeah.
All of the above. These are all crucial sequential gears in the process.
They really are. But knowing the sequence still leaves us with a pretty major practical problem. Where do the initial ideas actually come from?
That is the golden question.
Right, because if identifying missing data is the spark, where are we looking for that missing data? Question 3 asks just that. Source or sources of a research question is or are A, published literature, B, being alert to new ideas, C, careful observation and teaching, or D, all of the above.
The answer is D, all of the above. Inspiration really is
Or
everywhere.
it could just hit you anywhere.
Totally. It happens when you're reading existing studies and you notice a flaw. Or, it happens during teaching when a student asks a seemingly simple question that you suddenly realize science hasn't actually answered yet.
But not all sources are created equal, right? Because this brings us to question 23, which presents a really interesting scenario. It asks, which of the following is not an ideal source of a research question?
Oh, this is a tricky one for a lot of people.
Yeah, the options are A, reviewing published literature, B, attending conferences where latest findings are shared, C, observing keenly in the outpatient clinic, or D, mining existing data sets.
The correct answer here is B, attending conferences where latest findings are shared.
Wait, I have to push back on this.
I thought you might.
I mean, major medical or scientific conferences are literal gatherings of the top minds in a field. They're practically designed for idea generation. Why wouldn't that be an ideal source?
I know, it sounds super counterintuitive, but think about the nature of conference presentations. The researchers up on that stage, they are sharing completed findings, or at least data that is already well into the publication pipeline.
Okay, I see where you're going with this.
Right. If you sit in the audience and base your brand new research question purely on someone else's freshly revealed data, you are inherently behind the curve.
Oh, wow. Yeah, you're chasing the trend rather than setting it.
Exactly. The most novel, truly impactful questions stem from observing raw gaps, like directly in the clinic, or by deeply analyzing older literature, rather than just piggybacking on the shiny new results presented at a symposium.
Okay, I see the distinction now. You want to find the silence, not follow the noise. I like that. So once we find that gap, we have an idea. But an idea isn't a formal question yet, is it?
Not even close. It needs a lot of refinement.
Which perfectly lines up with question 10. It states, the process of refining the ideas into research questions begins with general uncertainty about a health issue and narrow down to a specific, concrete, researchable issue. True or false?
That is a true. I actually like to think of this process as a funnel.
A funnel? How so?
Well, you start at the wide top with a broad uncertainty. For instance, like, why do so many office workers complain of migraines? That's an idea, but it's way too vast to study.
Right, there are a million factors there.
Exactly. So you pour that idea through the funnel, restricting the variables until a specific concrete issue drips out the bottom. Something like, does blue light exposure exceeding 6 hours a day increase the frequency of migraines in adults aged 25 to 40?
Oh, I love that. So the goal is always specificity. And I guess that totally rules out the trap presented in question 30. It asks, which of the following is not a step in framing an ideal research question? A, literature review, B, peer review, C, broadening the initial question, or D, defining measurable outcomes?
Yes, the incorrect step there is C, broadening the initial question.
Because that would be going backwards.
Exactly. If you are broadening it, you're trying to push the idea backwards up the funnel. Broad questions just lead to vague methodologies and really muddy data.
So let's lock in the exact order of this framing process with question 20. It gives us 4 steps. Roman numeral 1 is review of state-of-art information. 2 is define measurable exposures and outcomes. 3 is raise a question. 4 is decide worth investigating by peer review. And we have to choose the correct sequence.
The correct sequence here is option CI342.
Okay, walk me through that.
Sure. First, you review the existing information, that's IPI, to ensure your idea hasn't already been thoroughly answered. Then you raise your specific question, which is 3.
And then peer review.
Yes. Next, and this is crucial, you run it by your peers, step 4, to see if the scientific community actually finds it worth investigating. Only after they validate the premise do you take the final step, 2, to strictly define your measurable variables and outcomes.
That makes a lot of sense. That peer review step acts like a quality control checkpoint before you commit all your resources.
Exactly. It saves you from building a skyscraper nobody wants.
Right. So we've figured out how to funnel a broad idea into a specific question. But that brings us to a harsh reality. Not all specific questions are actually good questions. Let's look at the criteria for evaluating them. In the materials, this is governed by the FINER acronym.
Yes, the finer criteria. It's a lifesaver.
Let's test this with question 18. All the following are components of FINER criteria for a research question, except E, feasible, B, reliable, C, novel, or D, ethical.
The exception here is B, reliable. Let's just break down finer for a second. It stands for feasible, interesting, novel, ethical, and relevant.
Okay, so where does reliable fit in?
But reliable is a critical concept in science, but it applies to the tools and tests you use. A thermometer is reliable if it gives the same reading every time. But a research question isn't reliable, it's the premise itself.
Oh, I see. That makes question 25 really straightforward. It asks, which of the following characteristics best describe a good research question? And the options try to trick us with similar sounding words. A, feasible, novel, ethical. B, feasible, noble, ethical. C, ethical, novel, intuitive. Or D, fantastic, novel, relevant.
Yeah, don't let them trick you. Strictly applying the acronym, the answer is A, feasible, novel, ethical.
Noble and fantastic are a bit subjective anyway.
Highly subjective. They're not scientific metrics. And intuitive can actually be a negative. I mean, some of the best science is deeply counterintuitive.
That's a great point. I actually want to look closer at the F in finer feasible, because question 11 asks to identify the incorrect statement about a good research question. It lists things like advancing knowledge, getting ethics approval, and confirming previous findings. But option D is feasibility should not be a criterion while developing research questions.
And that makes D the incorrect statement. Feasibility is arguably the most brutal hurdle of them all.
Brutal. How so?
Well, you could design a question that is incredibly interesting, completely novel, highly ethical, and deeply relevant. But if answering it requires a $1 trillion budget, a 20-year timeline, and, I don't know, a population of identical twins raised in zero gravity?
It's just science fiction at that point.
Exactly. It is a terrible research question because you literally cannot execute it.
Right. But does a good question need to sound like it was written by an academic robot? Question 8 asks which statement is incorrect. A, a good research question should be finer. B, a good research question should be in epidemiological terms. C, a good research question facilitates optimal design. Or D, a good research question will focus on one issue.
The incorrect statement is B. A good research question should be in epidemiological terms. This is such a massive misconception.
People think sounding smart makes the science better.
They do. But you do not need thick jargon to legitimize your work. In fact, if your question is buried in complex terminology, it often masks a lack of clarity. A good question should be understandable to anyone with a solid education in the broader field.
So clarity is king. And the ultimate function of this clear question is outlined in both question 7 and question 21. They essentially ask the exact same thing. A clear research question facilitates doing what? Choosing the optimal design, identifying the study population, or specifying the outcomes to be measured.
And both questions conclude that the answer is D, all of the above.
Because it's the blueprint.
Yes. The question dictates every subsequent step. If your question asks about long-term effects, it dictates a longitudinal design. If it asks about a specific drug, it dictates the population. The blueprint dictates the building materials.
I love that analogy. But the blueprint shouldn't include, like, the marketing pitch for the building, right? We'll take question 14. A research question states about what the results of the study might ultimately contribute to that particular field of science. True or false?
This is definitively B, false.
Yeah.
The research question is the laser-focused inquiry, like, does drug X lower blood pressure in seniors?
Keep it simple.
Right. The contribution to science, meaning how this will revolutionize geriatric cardiology and save millions in healthcare costs, that belongs in your background section or your rationale. If you cram the so what into the question itself, you completely lose that necessary precision.
Okay, so our question has passed the finer test. It's specific. It's not full of jargon. The next major hurdle is defining the nature of the question. Are we just taking a picture, or are we investigating a crime scene?
That's a great way to frame it.
This brings us to descriptive versus analytical studies. Question 24 asks, which of the following is true for a descriptive research question? A, involves observations to measure a quantity. B, involves comparison groups. C, tests the efficacy of interventions. Or D, requires hypothesis testing.
The true statement here is A, involves observations to measure a quantity. When we say descriptive, we mean it quite literally.
Just describing what's there.
Exactly. You are describing the current state of affairs. You are not comparing a control group to a test group. You're simply taking a snapshot of a population at a specific moment in time and counting what you see.
And the language we use gives away the game. Question 13 asks, which of the following verb is used in the statement of objective of a descriptive research study? A, estimate, B, determine, C, examine, or D, compare.
The correct verb is A, estimate. When you estimate a value, you are passively assessing a quantity that already exists.
Let's apply that. Question 5 gives us a scenario. If your objective is to estimate the prevalence of a health problem in a community in 2019, identify the type of research question. Is it analytical, descriptive, hypothetical, or experimental?
Because of the word estimate and the fact that you are simply looking at the prevalence, like how common a problem is, it is B, a descriptive research question.
Makes sense. Question 26 gives a slightly more specific example. State whether true or false.
Right.
A research study is conducted to estimate the seroprevalence of COVID-19 in Medabad City during April to June 2020. This is an example of analytical research question. True or false?
This one is B, false.
Even with fancy words like seroprevalence.
Yeah, even though words like seroprevalent sound highly technical, all it means is the percentage of individuals in a population who have a specific antibody in their blood serum.
So it's still just a snapshot.
Exactly. They are just drawing blood and counting how many people have antibodies. There's no intervention, no cause and effect being tested. It is purely descriptive.
Okay, so if estimate is the hallmark of a descriptive snapshot, what verbs do we use when we actually want to test cause and effect? Question 2 asks, which of the following verbs is preferably used in the statement of objectives of an analytical research study? A, estimate, B, determine, C, study, or D, describe.
For an analytical study, you want to use B, determine. When you determine something, you are actively settling a debate between variables. You are analyzing data to figure out if variable A actually influences variable B.
To reinforce that rule, question 9 asks if the statement is true or false. The verb estimate is used in the objective of analytical research studies.
And we know that is B, false. Keep estimate strictly in the descriptive bucket.
Got it. Let's test the analytical side with question 16. Identify the type of research question if the objective of a study is to determine the effect of tobacco cessation services on tuberculosis treatment outcomes among patients with tuberculosis. Is it descriptive, hypothetical, analytical, or experimental?
The answer is C, analytical research question.
Because of the word determine.
Exactly. The phrase determine the effect is the massive giveaway here. They are not just counting how many people have tuberculosis. They are analyzing the relationship between two moving parts getting quit smoking services and the success rate of tuberculosis treatment. They're searching for a link.
That sets us up perfectly for our final segment. We know our study type. Now we have to write the formal objectives and the hypothesis. If we connect this to the bigger picture, let's look at the pitfalls of writing objectives.
There are quite a few pitfalls.
Yeah. Question 27 asks, which of the following statement about study objectives is false? A, objectives are stated in scientific terms. B, objectives can be primary and secondary. C, each objective is written using multiple verbs. Or D, objectives should be specific.
The false statement is C. Each objective is written using multiple verbs. This is a trap that ensnares so many novice researchers.
Really? Why is that?
Well, they write an objective like, to estimate the prevalence of diabetes and determine its effect on vision. By using two verbs, they have combined a descriptive goal and an analytical goal into a single sentence.
Oh, I see. That sounds messy.
It is. When it comes time to design the methodology, it becomes a totally disorganized mess. The golden rule is one action verb per objective.
One verb per objective, and the choice of that single verb matters immensely. Look at question 29. How can the given study objective be improved? To understand the anemia in pregnancy is the answer A, using appropriate action verb, B, specifying the outcome measure, C, specifying the study setting and time period, or D, all the above.
The answer is D, all the above. I mean, the verb understand is practically useless in scientific research.
Yeah, how do you even measure understanding?
You can't. You can measure iron levels in the blood, you can estimate the prevalence of fatigue, but you can't measure a state of comprehension. An objective must be highly specific, measurable, and bound by a time frame.
Which brings us to the hypothesis. We've talked about questions and objectives, but where does the hypothesis fit in? Question 4 asks, which of the following is stated mainly for statistical purpose? A, research question, B, objective, C, research hypothesis, or D, all of the above?
The answer is C, research hypothesis. This is actually a fascinating translation process.
Translation process.
Yeah, you start with a question formulated in English, but a computer software program running a statistical model doesn't understand English. The hypothesis is the mathematical translation of your question. It's the formal predictive statement that a statistician will use to calculate probabilities and determine if your findings are actually statistically significant.
But does every single study require that mathematical translation? Question 15 states, purely descriptive research questions do not require a hypothesis. True or false?
This is true. Think back to our snapshot metaphor from earlier.
Right, the counting.
Yes. If your only objective is to estimate how many people in a city have a certain antibody, there is no relationship being tested. You aren't comparing anything, so there is no prediction to prove or disprove. You are just counting. Without a relationship to test, a hypothesis is entirely unnecessary.
Let's apply that logic to question 17. It asks, as per the following objectives, a hypothesis should be stated for which study? Option A, to determine the association of maternal smoking during pregnancy with respiratory infectious disease, morbidity, and mortality in infants. Option B, to estimate the lifetime prevalence of asthma. Option C, to describe the pattern of drug resistance. Or option D, to describe the temporal trend of malaria.
The correct option is A. Notice the language in options B, C, and D.
Yeah, estimate, describe.
Exactly. They're purely descriptive snapshots. Option Jorgen uses the verb central, determined to look at an association between maternal smoking and infant disease. Because it seeks to analyze a relationship between two distinct variables, it absolutely requires a testable hypothesis.
Now, regarding the timing of writing this hypothesis, question 12 lists characteristics of a good hypothesis. It should be simple, devoid of ambiguity, focus on the primary objective. But option D says research hypothesis should be written once the study is completed.
And that is the glaring exception. The answer is D. Research hypothesis should be written once the study is completed. That's the one that is not a characteristic.
I mean, if you do that, you're just painting a bullseye on the wall after you've already shot the arrow.
Exactly. It completely invalidates the integrity of the scientific method. A hypothesis is, by definition, a prediction. You cannot predict something after it has already happened. It must be established beforehand.
And the scientific term for beforehand is the focus of our final question, question 22. Characteristics of a good hypothesis are all, except T, there should be no ambiguity about the study variables. B, it should be stated a priori. C, it can be revised based on the study findings. Or D, it should specify one exposure and one outcome.
The incorrect characteristic is C. It can be revised based on the study findings.
Let's unpack that jargon in option B, a priori.
Sure. A priori is a Latin phrase that basically means from the earlier, or essentially before the fact. You must state your hypothesis a priori. If you run your study and your data completely contradicts your prediction, you absolutely cannot go back and revise your hypothesis so that it matches the data.
You just have to take the L.
You do. You must honestly report that the evidence did not support your hypothesis. That honesty is how the scientific record actually advances.
It takes discipline to accept that you were wrong, but I guess that's the whole point of the exercise. Wow. We have covered a massive amount of conceptual ground today.
We really have.
We walked through the true sequence of the research life cycle, learning that identifying the missing data is the spark that starts the whole engine. We learned how to funnel vague ideas into rigorous inquiries using the finer criteria, ensuring our studies are actually feasible to pull off. We decoded the secret language of verbs, discovering that estimating provides a descriptive snapshot while determining hunts for analytical cause and effect.
And we wrapped up with the math translation.
Exactly. We saw why the hypothesis must be locked in a priori, translating our question into the strict language of mathematics. You now have the underlying logic to completely master all 30 of these concepts.
You really have the blueprint now. But before we finish, I want to leave you with something to consider beyond just the mechanics of the methodology.
Oh, I like where this is going.
We've spent this entire time discussing how to carefully construct a research question that is safe, feasible, and perfectly aligned with the literature. But ponder this on your own. What happens when a researcher formulates a finer approved question, follows all the rules, and the resulting data completely shatters a deeply held scientific paradigm? How does the broader community react when the right blueprint accidentally builds a structure no one is prepared to see?
That is the thrilling part of science. You design the perfect map, but you never truly know what you are going to find when you start digging. Remember, long before the data is collected or the paper is published, every great breakthrough begins with the courage to simply ask a well-crafted question. Keep refining those ideas, keep looking for the missing pieces of data, and keep drawing up those blueprints. Until next time.